So see, in that case, capacitance of air will be the same, epsilon naught A by D. Charge will be, this is the case when, this is the general case. Okay, this we already know. I'm just making you revise the formula. Capacitance is what? Epsilon naught A by D. Charge is C into V. Potential difference is V naught. Electric field is V by D, because electric field according to the potential gradient is this. This is what we've already studied. Okay. If the case says that battery remains connected and plates are filled with dielectric constant K, see what all changes will be there. Capacitance, which earlier was epsilon naught A by D, now will become K times K epsilon naught A by D. Okay, it will become K times. Second, charge, which was C naught V naught, here it will become K times C naught V. Okay, it will be multiplied by K. Then potential remains the same here. Whatever was the potential difference here, even after connecting the battery, okay, your capacitor is still connected, potential remains constant. And see, electric field is potential by difference. So if potential remains constant, so your electric field also remains constant. So when it says what happens when battery remains connected and a dielectric constant slab is put, capacitance increases by K times, charge increases by K times, potential remains the same, electric field remains the same. Clear? Now, if the battery is disconnected, and space is filled with dielectric capacitance, okay. So, capacitance will increase K times, K T naught, it will increase. Charge here will remain constant. Okay, charge here will remain constant. What was remaining constant here? The potential. What will remain constant here? The charge. Okay, the charge will remain constant here. It won't increase by K times or anything. Capacitance increases K times in both the cases. Charge remains constant. So potential, it is Q naught divided by Kc naught. How? Potential is charged by capacitance. Capacitance is K times Kc naught, right? So potential will be V naught by K. So it decreases by K times. Similarly, electric field is potential by distance. So electric field becomes E naught by K. Is it clear? Are you awake? Is it clear till here?
Yes.
Remember like this. See, when the battery is connected, pay attention, Basmi. When the battery is connected, capacitance increases, charge increases, potential remains the same, electric field remains the same. When the battery is disconnected, capacitance will increase, but charge will remain the same. Potential decreases, electric field decreases. Okay? So this comes, then I'll tell you how we begin with the sharing of the combination of capacitors. Okay, please start writing it from here.
Ma'am, can you scroll down? Ma'am, I'm done. Done, ma'am. Ma'am, I'm done. Done, ma'am.
See, Basmi, now when we start with the division of charge and potential, before we go on to the capacitance, how the capacitors are connected in series, in parallel, and everything, there are certain basic things that you need to know in the second chapter itself. And see, whatever I'll tell you about the charge is valid for current in your current electricity. So, major portion of your resistance, the resistors will also be covered. I'll not cover it like this only. I'll discuss that in resistors again. But right now, when I am discussing whatever I'm discussing about charge and potential, it's exactly valid for your resistors. See, you should understand first how a charge divides. See, charge never divides when the wire is bent or anything. Like, see, if I have a straight wire like this, across it, the charges that will be flown, if Q is flown here, Q will be flown here also. If I bend the wire like this, so if Q amount of charge was going from here, down also Q will go, till here also Q amount of charge will go. Your bending of wire doesn't affect your charge, okay? Or if I say I put a device, let's say I have put a capacitor, two capacitors or a single capacitor, this also doesn't affect the charge. If Q amount of charge is flowing from here, across this also Q will flow, across this also Q will flow. Means across your devices, charge doesn't get affected. This is what is the rule for the charge. You put any device, when I use the term device means there are three devices that you will be dealing with. In the second chapter, you will study about capacitors. In the third chapter, you will study about resistors. And in the 6th chapter, you will study about the inductors. So all these devices do not affect our charges. So how does a charge get affected? How does a charge get affected, or how does a charge divide? Only on branching. Branching means when from one wire, two segments are being drawn out. It's not the bending of wire. You are putting another wire and adding a branch of it. So like this, if you have a wire like this. So here in this case, let's say Q charge was coming. Here it will be Q1, here it will be Q2. And it's not necessary that Q1 and Q2 are always equal. They can be unequal also. Q1 can be equal to Q2 also. This depends if whether equal division is being done or not. Like, let me give you an example. This is a capacitor here. Then this, there is a capacitor. Here is another capacitor like this. Now, let's say this is C1, this is C2, this is C3. So look, Q amount of charge is coming. Tell me, Basmi, here will it be Q or will it change?
Will change
It will change. Why?
because there's a capacitor.
So did I not tell you that capacitors doesn't affect
Oh
your,
yeah. So it's the same. It's the same.
will be the same. Now here will it be the same in this file?
No, it's getting branched. So
It will be the same.
no, it won't be the same.
It won't be the same. Yeah. Here it will be, let's say, some Q1. Okay, if this is Q1, what will be the charge here, Basmi?
Q1.
Q1. Yes, Basmi. Right. Okay, Basmi, tell me, let's say this is Q2 because here there is branching this portion. Basmi, tell me here what will be the charge?
Q2 itself.
Correct. Understood the division of charges?
Yes, ma'am.
Okay. But potential doesn't divide like this. When we have the potential doesn't divide like this. Potential gets affected by devices. Like if I have a straight wire, then obviously the potential will be the same. Here, if it is VA, here also it will be VA because it's the same wire. Branching doesn't affect our potential, nor bending affects. Suppose this is the wire. So if I'm talking about the potential here, let's say VA, this will also be VA, this point will also be VA. Let's say the branching has occurred. This point is, let's say, VA. Here also it will be VA. Here also it will be VA. Okay. Your potential gets divided on devices interaction. Means as soon as there's a devices interaction. Like if I tell you this, let's say here I have a capacitor. This is valid for resistors also. Like if I have a resistor, same thing. If potential is VA here, the potential will be some VB here. It will be different. Like if I now give you an example from here, the same example which I was considering for the previous case. Let's say this is a capacitor and this is a capacitor C1, C2, C3. So this is, let's say here some potential is there VA. Tell me, here will it be same or different?
Different, ma'am.
Different, very good. Okay, if this is VB, will it be same or different here?
Same there.
Same, very good. Will it be same or different here?
Different.
Different. Will it be VB or something else here?
VB itself.
It will be VB. Same. And here,
VC.
What?
It's a new resistor, not VC. It will be VD or something. Yeah.
VD or something, exactly. Let's take it VD. So this is clear. This part is clear.
Yes, ma'am.
Okay, very good, Basmi. If you've understood this, now just one thing. See, before you start writing, in case of charges, you can replace this same knowledge with the knowledge of current. Okay, I'll just put an
Ma'am.
asterisk and I'll just write current also so that you remember it. Because I'll not discuss then everything in so detail in current electricity. Then that chapter will go off. Here we'll do it in detail, the basics. So same thing for current. Now understand, when the charges in capacitors or current in resistors remain the same, it is series combination. Series combination is not just that you are putting capacitors or resistors in line with each other. You will have certain circuits where it will be very difficult for you to identify whether it's a series combination or it's a parallel combination. Okay, so best method is that see the charge. When the charges remain the same in case of capacitors or the current remains the same in case of resistors, it's the series combination. And if you see potential remains the same, voltage remains the same, it is parallel combination. So in detail, I'll
Okay,
start
ma'am.
with series and parallel, but you write down these examples. And if you're able to identify them properly, you'll not have any trouble with any of the circuits. We'll see a lot of circuits and lots of methods. Some circuits I'll teach you here in capacitors, rest of it, various we'll see in current electricity. Okay?
Okay, ma'am. Done, ma'am. I'm done now. I'm done, ma'am.
See, Basmi, now let's start with the series combination of the circuits. See, we will be doing the basics. As I've told you, this part I'll not be doing again in current electricity. Means this explaining part. We will practice lots of circuits directly in the chapter current electricity. Okay, because you have your exam, that's why I'm emphasizing on that current electricity also right now. See, in series combination, charges remain the same. So you have various capacitors, 1, 2, 3, 4, 5, 6, n number of capacitors are connected. And each of the capacitors have their own individual capacitances, right? C1, C2, C3, C4, C5, Cn. And they have their individual potentials also, V1, V2, V3, V4 till Vn. But one thing that remains the same in all of the capacitors is the charge. What we'll do, I have different potentials. Let me find out the net potential. The net potential will be, the equivalent potential of the circuit will be V1 plus V2 plus V3 up till Vnth. N number of, it can be 4, it can be 5, it can be 6, there can be any number of resistances that are connected. Okay, now you know potential, your capacitance is equal to charge by potential. So potential will be equal to charge by capacitance. Equivalent potential will have equivalent charge, but charge is the same by equivalent capacitance. V1 will be Q by C1, not Q1 because Q is the same, plus V2 will be Q by C2 because charge is the same, capacitance is different, so I've put C2 plus Q by C3 like this. Then up till Q by C and see all the charges till since they are same on both the sides, they'll get cancelled. I'll have the value of the individual capacitances as 1 by C1 plus 1 by C2 plus 1 by C3 up till 1 by C nth. This is the smallest derivation which usually doesn't come in the exam. The applications based question comes. Now see, if I want to get the net charge Q equivalent, I'll write C equivalent into V. Similarly, if I want, because charge is the same for all of it, so I can just write C equivalent into V. What if I want the potential only in the first capacitor? So for the first capacitor, I'll write it as Q by C1. If I want the potential for the second one, I'll write it as Q by C2. Equivalent Q by C equivalent, like this. Whichever is required, you will take that individually. Likewise, you can calculate the energies also. Half C equivalent V square will be the total. This is the total potential, total energy. This is the total energy stored. Okay, or Q square by 2C equivalent. But if I want the energy of only the first capacitor, which has C1 V1 as the potential, so I'll take it as half C1 V1 square. U2 will be half C2 V2 square. Likewise, U1 can be a Q square by 2C1, U2 will be Q square by 2C2, like this, depending upon the individual. When it is individual, take all the data of the individual things, but just take charge commonly for all. And whereas when you have the energy, then you can calculate C equivalent. Write it, then let's practice one question. Is that clear to you, Basmi?
Yes, ma'am.
All right, please write it.
I'm done. I'm done.
See, this question has two capacitors, 10 farad and 5 farad connected to a 10-volt battery. Now we have to first find the C equivalent. So, Basmi, tell me the steps. For C calculation of C equivalent, what is the formula that should be used?
One by C1
Yes. Then,
plus 1 by C2.
correct. So formula will be 1 by C1 plus 1 by C2. Now look, 1 by 5 plus 1 by 10. So this is 3 by 10. This is 1
Yes,
by
ma'am.
C equivalent. But we need C equivalent. We don't need 1 by C equivalent. So we will inverse it. This is the answer. Do not forget to leave means to reverse this. If you forget, your answer will be incomplete. All right, now total voltage across the circuit. What do you think is the total voltage across the circuit?
And
What's the total voltage?
10.
10. See, this is the total voltage. This is supplying. From here, the charges will move. So total voltage will be 10 volt.
10.
Total charge stored. See, I told you the formula. When you want the total, something total, so you will use everything total. So total charge means total charge will be the total capacitance into total voltage. What's the total capacitance?
Uh, 10 by 3.
10 by 3 is equivalent 10 by 3. Voltage is 10. So charge becomes 100 by 3 coulomb. This is the total charge, right?
Yes, ma'am.
Okay. Third part we've done. Fourth, charge stored in each. Now this you tell me. What will be the value of charge stored in each? Q1 and Q2. How should we calculate? Hmm? This is the total charge. How will you get the charge in each?
Separately,
What, Basmi?
is it by putting Q by Q1?
This is a series combination. See, in series combination, your charges remain the same. So Q1 will equal to Q2 is whatever is Q equivalent. All the charges will be the same. That's what we studied. This will still be 100 by 3 coulomb only. Whatever charge is coming here from here, it will be Q across this also, Q across this also, Q across this also. Got it?
Yes, ma'am.
Fifth part says voltage across each, but voltage will be different.
Mm.
Okay, V1 will be charge is the same, but capacitance is different. So 100 by 3 into first capacitance is 5. So this becomes 20 by 3 volt. Second one,
Yes, ma'am.
V2 will be Q by C2. That is
C2.
100 by 3 into 10. So this becomes 10 by 3 volt. Now, in order to check whether you're right or not, see, total potential, you know, it is 10 volt.
Yes, ma'am.
So you should check whether you're getting 10 volt or not. If I add V1 and V2, I'll have 20 by 3 plus 10 by 3. That is 30 by 3,
10, 30
10.
by 3. But
Means
you
we
have to
have
get
divided the potential equally. This is how the voltage is getting divided. And why? See, capacitance is different, C1, C2. Voltages are different, V1, V2. But charge is the same. This is the whole fundamental concept about the series combination. Okay?
to, ma'am.
You write it, then I'll introduce parallel combination and then we'll do mixed questions because you will not have such plain questions. Write it first.
Okay, ma'am. Can you scroll down?
Ma'am, I'm done.
Okay, let's come to the parallel combination. Now, see in your parallel combination, the potential remains the same, right? And charges will be divided in all of them. Okay. So when I take the net, see now I'll take the net charge because all the charges will give me the equivalent charge. Equivalent charge will be Q1 plus Q. In the previous case, this was the same. Now this is different. So this will be Q1 plus Q2 plus Q3, 4, 5, 6 up till Q nth. Now Q is equal to CV. So Q equivalent will be C equivalent V. V means the V equivalent and V is the same. C1V plus C2V plus C3V. Look, V is remaining the same in every of it because your potential remains the same. Plus till Nth CV. All the potentials get cancelled. C equivalent becomes C1 plus C2 plus C3 till you just add them. Just add them. In the series connection, you have to take the reciprocal addition. Here you can just directly add it. Now let's practice a question. Then you can write it. These two are connected in parallel. So look, 5 and 10. So when I write 1 by C equivalent, this will, they are in parallel, so I'll just add them. So C equivalent will be C1 plus C2. C1 is 5, this is 10, which is equal to 15 farad. Second thing is total voltage. Can you tell me the total voltage?
10.
How much?
Ma'am, 10.
10. Total voltage will be 10 volt. Okay, can you tell me about total charge? how to calculate. This is the method.
Q is equal to CV.
Q equivalent will be C equivalent into V. C equivalent is 15, total voltage is 10. So this
10.
becomes
So
1.
150.
Okay. Next part, voltage across each. This answer.
That's 10 each.
How much?
10.
10. Very good. V1 will be equal to V2, which is equal to V equivalent. That is still equal to 10 volt only. Correct. Coming to the fifth one. Charge in each.
Charge will change.
Charge will change. Q1 will be C1 into V. So this Q was C1 is 5.
5.
Q, this is 5 into 10, which is 50 coulomb. And Q2 is C2 into V, 10 into 10, which is 100 coulomb. See, when I add it, Q1 plus Q2, 50
I'll get 1.
plus 100. I'm getting 150 coulomb, the total charge back,
Yes, ma'am.
right? So this is how we have to calculate. Okay, I've put energy also in each, in this one. Energy in each. When it says energy in each part. Energy in each.
Half CV square.
C. C will be C1. Okay.
Oh yeah, C1V square.
C1 B square. Correct. This will be half. C1 is 5, V is 10. So this becomes 100. So this is 50. 50 into 5 is 250 joules. Okay. U2 will be half C2 V square. So half 10 into 100. That is 500 joules. Right. Now, last part says total energy stored. So what we can do, two methods are there. Since you know the individual energies, you can straight away add them,
Total.
right? U1 plus U2, that is 250 plus 500, that is 750 joules. Or you can use this also, half into C equivalent into V. So half into C equivalent was 15. Oh, sorry, half CV square. And this will be 100. 1500 divided by 2 is 750. Or any of it you can. Okay. Yeah.
Yes, ma'am.
Okay. All right. Write down this one also.
Can it hold up? Can it hold up?
Done.
Yes, ma'am.
See, now we just have to practice different cases. That's all what is left from this chapter. I'll try to take one extra class this week so that this chapter is at least completed, and from Friday we can start with current electricity. Because we need to complete current electricity and at least start with magnetism before your test. So we need extra classes first. Okay. So let's see when we can
Okay.
have the, or you tell me a time when we can have the class when you don't have any other class. You take bio here. Yes.
What did you say?
Hmm?
Ma'am, in the end, you said something. I couldn't hear it.
Sorry.
Ma'am, in the end, you said something, right? Before I started speaking, what were you telling?
No, no. I was saying that you take bio here. I think you have bio classes
Ma'am.
also.
No,
No.
ma'am. I'm
Okay,
a
you
bio
are a
student.
same student only. So you any other subject that you take here at Learnivio?
No, ma'am. Only physics.
Only physics. So are you available in the weekday or any morning time or any time? Any day.
Tomorrow morning I'm available. Morning, I think after 1:30, it's fine. At one
When
thirty also it's okay.
when
1:30, is it okay?
1:30 KSA or
Tomorrow.
UAE?
No, mama, you Indian time.
1:30 IST.
Hmm.
Yeah, this is fine for me. When? Tell me the day.
Tomorrow.
Tomorrow, 1:30 you're
Hmm.
available.
Yes, ma'am.
Tomorrow do you have an off?
Yes, ma'am. My off is on
Okay.
Saturday and Sunday. Tomorrow
All right.
morning,
Yeah.
after
You are in Dubai, no, Basmi? Are you in Dubai?
ma'am.
Okay, so there now the weekends have changed. All right. Then 1:30 we can have the class, not tomorrow. All right.
Hmm.
1:30 IST. We'll complete this chapter tomorrow. Okay,
Okay,
few
ma'am.
things are there that I want to discuss that I have to discuss with you. I'll discuss. But because the whole week you will have your school, so we won't be having any other classes, right?
Yes, ma'am.
Okay, no issues. We'll complete the chapter by tomorrow. Okay. See, this is a capacitor connected with two other capacitors. Now, these two are connected in parallel and their resultant is connected in series with this, right? So first we'll reduce these two. Let me name them. This is 1, this is 2, this is 3. So we know that 2 and 3 are in parallel combination. So what will be the C equivalent? C23 means between these two.
Will be one
1. Why?
one C two plus one by C three. Wait, not one. It's just direct. No, it's direct.
What? Yeah,
One
so
plus C.
it will be,
C1 plus C2 plus C3.
that is, what's the answer? Tell me the answer
Uh,
directly. How much?
15 into raised to minus 6.
Very good. See, they are connected in parallel. In parallel, we directly add them. You can get confused in current electricity. In current electricity, if you've studied, you will notice that the formula is different. Series one
Yes, sir.
directly added, parallel is. So be very careful, capacitors, because in your test you have both the chapters. So you have to remember both the things. Anyways, that we'll discuss later. So 2 and 3 are in parallel, C2, 3. So this will be 5 plus 10, which is 15 microfarad only I'm taking. Now I can reduce this circuit and I can write this as 10 microfarad, and here I, instead of 2, 3, I can write this as 15 microfarad, right? The rest of them with the battery, which is 10 volt. Now, like here in this one, these two were connected in parallel. Now, these two are connected in
Series.
series. Finally, the answer will be reciprocal addition of it. That is 1 by
Mm-hmm.
equivalent is 1 by 10 plus 1 by 5. Or directly you can say 10 into 15 divided by, right? Which is 150 divided by 25. So 5 into 5, 5 into 30, 6. 6 microfarad. Correct? Yeah.
Yes, ma'am.
Equivalent will be 6 microfarad. We will do more questions. But it is now we are doing combination of series and parallel. Individual basics we
Mm.
have studied. Please write down this one.
Yes, ma'am. Ma'am, can you scroll down?